August 24th, 1978, 2:47 p.m. Mountain Time. Deep beneath the Wyoming prairie, in a classified missile silo designated A8, Technical Sergeant Marcus Chen was conducting a routine electrical check on America's most sophisticated nuclear weapon. 6 volts of standard electrical current, harmless as a car battery. The Minuteman III, intercontinental ballistic missile, had 17 independent safety systems. Military briefings assured personnel that accidental detonation was mathematically impossible. The Mark 12A nuclear warhead, sitting 170 feet underground, packed 335 kilotons of destructive power, 22 times more powerful than Hiroshima. But those 17 backup systems made it absolutely safe. Every electrical pathway had been mapped. Every failure scenario had been calculated. The odds of catastrophic cascade failure were less than 1 in 50 million. At 2:47 p.m., 6 volts of routine testing current found a pathway that didn't exist on any schematic. One by one, those 17 independent safety systems began failing in sequence. The warhead's conventional explosives detonated with the force of 2,000 pounds of TNT. A 740-ton concrete blast door was hurled 200 feet into the air. Radioactive debris scattered across 25 acres of rangeland. And Strategic Air Command told the world it was just a minor guidance malfunction. The most dangerous nuclear weapons accident in American history had revealed something terrifying about the weapons designed to protect us. Technical Sergeant Marcus Chen had been staring at the same electrical schematic for 3 hours, his coffee growing cold in the sterile fluorescent lighting of the maintenance bay at Launch Facility A8. The blueprint spread across his metal desk showed the guidance system for Minuteman III, serial number 77492, a 40-foot-tall intercontinental ballistic missile that had been sitting in its underground silo since 1975. Chen traced his finger along the voltage pathways, following the 6-volt testing circuit that would verify the missile's guidance computers were functioning properly. It was routine maintenance, performed hundreds of times across the Minuteman fleet without incident. But something bothered him about diagram section J12. The electrical pathway showed a connection between the guidance system's test circuit and the primary safety interlock that seemed to bypass the main isolation switch. Chen pulled out his personal notebook, a habit that irritated his superiors but had saved him from equipment failures before, and sketched the circuit from memory. The voltage flow didn't match what the official documentation claimed was impossible. Sergeant Chen, you ready for the systems check? Staff Sergeant Rodriguez appeared at his shoulder, clipboard in hand. Colonel Mitchell wants this wrapped up by 1500 hours. Chen looked up from his notes. I need to verify something in the electrical specs first. This guidance test circuit, it shows a potential feedback loop that could affect the safety systems. Rodriguez glanced at the schematic and shrugged. Chen, these birds have been flying for 8 years, 17 independent safety systems. The eggheads at Boeing designed them to be foolproof. You're seeing problems that aren't there. Maybe, Chen said, but he kept his notebook open. But if there's a voltage pathway that could bypass the primary interlock during testing, we need to document it before we energize the system. Look, the safety briefing was clear. Mathematical impossibility of accidental detonation. Period. Rodriguez tapped his clipboard impatiently. We follow the checklist, run the test, file the report. That's how the Air Force works. Chen had heard the same assurances during his 3 years working Minuteman electrical systems. The Mark 12A nuclear warhead buried 170 feet beneath the Wyoming prairie contained enough explosive power to vaporize downtown Cheyenne. But the safety systems had been designed by the brightest minds in nuclear engineering: primary safety interlock, environmental sensors, altitude detection, G-force monitors, a cascade of 17 independent checkpoints that would prevent accidental detonation under any conceivable circumstances. The problem was that Chen could conceive of circumstances the designers hadn't considered. At 14:30 hours, Chen descended into the missile silo via the personnel elevator, carrying his testing equipment and his growing unease. The Minuteman III stood like a mechanical giant in its concrete tomb, its white paint gleaming under the harsh work lights. The Mark 12A reentry vehicle sat atop the missile like a black arrowhead, containing 335 kilotons of nuclear fury, 22 times the destructive power of the bomb that had leveled Hiroshima. Chen connected his testing leads to the guidance system interface panel, double-checking each connection against his schematic. The 6-volt electrical current that would verify the missile's navigational computers was identical to the power source in his personal radio. Harmless under normal circumstances. But if his analysis of the electrical pathway was correct, those 6 volts could travel through circuits that weren't supposed to be connected. Guidance system test commencing, Chen spoke into his radio headset, his voice echoing in the concrete chamber. All personnel clear the silo level. He activated the test sequence. 6 volts of direct current flowed into the Minuteman's guidance computer, checking the gyroscopes and accelerometers that would navigate the missile to its target 6,000 miles away in the Soviet Union. For 2.2 seconds, everything proceeded normally. The guidance computer processed the test signals. The voltage meters showed nominal readings. The safety systems remained in standby mode. Then the electrical feedback began. Chen watched his voltage meter spike as current flowed back through the circuit he'd identified on the schematic, the pathway that wasn't supposed to exist. The primary safety interlock, designed to prevent any electrical signal from reaching the Warhead's arming systems, registered the feedback as an authorization signal. A cascade of electronic confusion rippled through the missile's safety network. Environmental sensors programmed to verify that the missile was airborne before allowing warhead activation detected electrical noise that resembled altitude changes. The backup G-force detectors registered vibrations from the silo's ventilation system as acceleration forces. One by one, 17 independent safety systems began failing in a sequence that no single engineer had ever modeled. At 14:47 hours and 23 seconds, the conventional explosives surrounding the Mark 12A's nuclear core detonated with the force of 2,000 pounds of TNT. The explosion hurled the silo's 740-ton concrete blast door 200 feet into the Wyoming sky like a massive stone coin. The reinforced walls of the underground chamber cracked and buckled. Chen, thrown against the far wall of the personnel access tunnel, felt the earth shake as 60,000 pounds of concrete and steel collapsed into the missile bay. Radioactive debris from the Warhead's plutonium core scattered across 25 acres of prairie grassland, contaminating an area that would require months of cleanup. Chen pulled himself upright, his ears ringing from the blast, and stared at the smoking crater where America's most sophisticated nuclear weapon had been sitting moments before. The electrical pathway he'd identified, the one that wasn't supposed to exist, had just proven that mathematical impossibility was a dangerous assumption when applied to weapons capable of ending civilization. Above ground, Soviet reconnaissance satellites detected the explosion signature within minutes, their sensors recording electromagnetic patterns consistent with nuclear weapons testing. In Moscow, intelligence analysts began preparing reports on apparent American nuclear weapons activities in Wyoming. The Cold War's delicate balance of terror had just shifted, though neither side yet understood how completely. Colonel James Mitchell received the initial damage report while reviewing SALT II negotiation briefings in his office at F.E. Warren Air Force Base. The call from Launch Facility A8 came through the secure line at 15:03 hours, 18 minutes after the explosion. Sir, we have a broken arrow situation at A8. The Mark 12A warhead has detonated. Conventional explosives only. Repeat, conventional explosives only. Sergeant Chen is alive, but the silo is destroyed. Mitchell set down his briefing folder and stared at the red telephone for several seconds before responding. A broken arrow, military terminology for a nuclear weapons accident, was every wing commander's nightmare. But a warhead detonation inside its own silo represented something far worse than a nightmare. It was a strategic catastrophe that could unravel America's entire nuclear deterrent. Within 20 minutes, Mitchell was airborne in a UH-1 Huey helicopter, flying over the Wyoming prairie toward the smoking crater that had been Launch Facility A8. From 500 feet, the destruction looked like a battlefield. The massive concrete blast door lay cracked and twisted 200 feet from the silo opening. Emergency vehicles surrounded a 60-foot crater where the underground missile facility had collapsed. Geiger counters in the helicopter's cabin clicked rapidly as they detected radioactive contamination scattered by prairie winds. Mitchell's radio crackled with updates from Strategic Air Command headquarters in Omaha. Soviet satellite coverage of the area had increased dramatically in the past hour. Moscow's intelligence services were undoubtedly analyzing every detail of the explosion, looking for weaknesses in American nuclear capabilities. The SALT II negotiations, scheduled to conclude within months, hung in the balance. Any admission that America's most advanced nuclear weapons could accidentally detonate would hand the Soviets a devastating propaganda victory and potentially compromise the entire Minuteman III program. The helicopter landed 50 yards from the silo perimeter, beyond the immediate radiation zone. Mitchell climbed out, wearing full protective gear, his radiation dosimeter already registering elevated levels. Technical Sergeant Chen stood near the emergency command post, his uniform torn and dust-covered but otherwise uninjured. The sergeant's survival seemed miraculous given that he had been inside the silo when 2,000 pounds of high explosives detonated. "Sergeant, I need your initial assessment," Mitchell said, his voice muffled by the respirator mask. "What happened down there?" Chen pulled out his notebook, its pages smudged with concrete dust. "Sir, I identified a potential electrical feedback loop in the guidance system testing circuit. When I initiated the routine 6-volt check, current flowed through an undocumented pathway that triggered cascade failures in the safety systems. 17 independent failsafes failed in sequence over 2.3 seconds. Mitchell felt his stomach tighten. Cascade failure of nuclear safety systems was supposed to be impossible, not just unlikely, but physically impossible according to Sandia National Laboratory's engineering analysis. "Sergeant, are you certain about this electrical pathway? Could this have been equipment malfunction or human error?" "Sir, I documented the circuit anomaly before beginning the test. The electrical schematic shows a connection that shouldn't exist but does. The safety interlock interpreted the test voltage as an authorization signal." Chen's voice was steady, but Mitchell could see the implications registering in the sergeant's eyes. If one Minuteman III had this vulnerability, the entire fleet of 450 missiles might be at risk. The immediate crisis was containment. Project Crested Ice, the classified cleanup operation, would require 300 personnel in full radiation protection equipment. The operation would cost $5.7 million and take 6 months to complete. Impossible to hide from Soviet satellites. Impossible to explain as routine maintenance. The radioactive contamination alone would require excavating and replacing 25 acres of topsoil. Mitchell walked to the crater's edge and stared down at the twisted remains of America's most sophisticated nuclear delivery system. The Mark 12A Warhead's plutonium core lay scattered in fragments across the crater floor, each piece glowing faintly in his radiation detector. The conventional explosives had created a localized nuclear disaster without the massive fireball of a true nuclear detonation, but the political and strategic implications were potentially more dangerous than a full nuclear explosion would have been. His secure radio buzzed with a priority message from Strategic Air Command. General Richard Ellis, SAC commander, was flying to Cheyenne to assess the situation personally. The Pentagon wanted immediate recommendations on information control and damage assessment. Most critically, they needed to know if this accident represented a systemic vulnerability that could affect other Minuteman III missiles. Mitchell made the decision that would define the next phase of the crisis. "This is Wing Commander Mitchell to all Crested Ice personnel. Classification level is Top Secret Special Access Program. Official designation of this incident is guidance malfunction with no nuclear involvement. All personnel are reminded that discussing classified information with unauthorized individuals is punishable under the Uniform Code of Military Justice." The cover story began taking shape within hours. Strategic Air Command's Public Affairs Office would report a minor electrical malfunction during routine maintenance at Launch Facility A8. The cleanup operation would be described as a routine exercise involving simulated radiation procedures. The massive concrete blast door hurled across the prairie would be explained as controlled demolition of obsolete silo components. But Mitchell knew the cover story would only work if they could prevent the Soviets from understanding what had actually happened. Soviet reconnaissance satellites had recorded the explosion signature and the subsequent radiation cleanup. Moscow's nuclear intelligence analysts would be working around the clock to determine whether America had experienced a nuclear weapons accident or a nuclear weapons test. The difference would shape Soviet strategic planning for the next decade. As evening approached, Mitchell stood in the temporary command post reviewing damage assessments and casualty reports. Miraculously, no one had been killed in the explosion. Chen's survival seemed to violate the laws of physics as thoroughly as the Cascade safety failure itself. But the strategic damage was only beginning. Within hours, Soviet intelligence would have preliminary analysis of the explosion. Within days, they would be demanding answers through diplomatic channels. And within weeks, the SALT II negotiations could collapse if America couldn't maintain the fiction that its nuclear arsenal was completely reliable and under perfect control. The most dangerous nuclear weapons accident in American history was about to become a test of whether America could keep its most devastating military secrets while learning from its most catastrophic failures. 3 days after the explosion, Chen descended into the damaged silo wearing full radiation protection gear, leading a 5-man technical investigation team tasked with understanding how 17 independent safety systems had failed in Cascade. The concrete walls bore scorch marks from the conventional explosive detonation, and twisted metal fragments from the Mark 12A warhead lay scattered across the crater floor like radioactive confetti. Chen's radiation dosimeter clicked steadily as he approached the remains of the guidance system interface panel. The investigation required painstaking reconstruction of the electrical failure sequence. Chen and his team worked in 2-hour shifts due to radiation exposure limits, carefully documenting each damaged component and tracing voltage pathways through melted wiring harnesses. The guidance computer's memory banks had been destroyed in the explosion, but the electrical connections themselves told the story of how a routine 6-volt test had triggered the most sophisticated nuclear safety systems to fail in perfect sequence. Dr. Sarah Williams from Sandia National Laboratories arrived on the 4th day, bringing advanced electrical testing equipment and 3 decades of nuclear weapon safety expertise. Williams had helped design the environmental sensors and safety interlocks that were supposed to make accidental warhead detonation physically impossible. She knelt beside Chen in the contaminated silo, examining the twisted remains of her own engineering work. "This pathway shouldn't exist," Williams said, pointing to a section of damaged wiring that connected the guidance system to the primary safety interlock. The original design specifications required complete electrical isolation between test circuits and safety systems. But I'm seeing direct connectivity here. Chen showed her his notebook documentation of the circuit anomaly. "Doctor, I identified this connection before the test, but according to the official schematics, this wiring configuration was impossible. The safety interlock was designed to prevent exactly this kind of electrical feedback." Williams studied Chen's circuit diagrams for several minutes, cross-referencing them against her own technical specifications. The problem became clear as she traced the electrical pathways on paper. The Mark 12A's safety systems had been designed in the early 1960s when electronic components were larger and simpler, but the guidance computers had been upgraded in the mid-70s with miniaturized circuits that generated electromagnetic interference patterns the original designers had never anticipated. "The issue is circuit density," Williams explained, sketching a new diagram in her field notebook. "When we miniaturized the guidance electronics in '75, we created electromagnetic feedback loops that didn't exist in the original design. The 6-volt test signal generates radio frequency interference that the safety interlock interprets as an authorization code. The technical team spent the next week mapping every electrical pathway in the damaged system. What they discovered challenged fundamental assumptions about nuclear weapon design. The Cascade failure had followed a precise sequence that revealed hidden vulnerabilities throughout the safety network. The primary safety interlock had failed first, interpreting electromagnetic feedback as a valid launch authorization. The environmental sensors designed to verify airborne status before warhead activation had been confused by electrical noise that resembled altitude changes. The G-force detectors had registered structural vibrations from the silo's ventilation system as acceleration forces consistent with ballistic flight. Most disturbing was the discovery that the backup timer system, the final failsafe designed to prevent accidental detonation under any circumstances, had actually been reset by the cascading electrical signals. Instead of preventing the explosion, the sophisticated electronic safety network had enabled it by creating an artificial launch sequence that convinced the warhead it was following proper detonation protocols. Chen realized this wasn't a design flaw in the traditional sense, it was an evolutionary problem. Electronic systems had become so sophisticated that they could create failure modes no single engineer could anticipate. Nuclear safety required not just multiple backups, but entirely different approaches to safety system design that assumed complex electronics would interact in unpredictable ways. Williams began developing a comprehensive analysis of similar vulnerabilities across the Minuteman III fleet. Computer modeling revealed 847 potential electrical pathways that could trigger cascade failures in other missiles. Each pathway represented a different combination of circuit interactions that could bypass safety systems during routine maintenance or testing procedures. America's nuclear deterrent was an engineering marvel built on hidden vulnerabilities that multiplied with every technological upgrade. The investigation team's findings were classified at the highest possible level and transmitted directly to Strategic Air Command headquarters. General Ellis reviewed the technical analysis personally, recognizing that the A-8 accident had revealed systemic problems that could affect the entire nuclear arsenal. The Minuteman III program represented a $20 billion investment in America's strategic deterrent, but every missile in the fleet potentially contained the same electrical vulnerabilities that had caused the Wyoming explosion. Chen's recommendation was radical in its simplicity: replace centralized safety systems with distributed independent monitoring networks. Instead of 17 interdependent fail-safes that could cascade into failure, design 70 simple, isolated safety checks that operated on completely different principles. Make the system so diverse that no single failure mode could propagate across multiple safeguards. The solution wasn't more sophisticated electronics, it was simpler, more robust isolation between critical systems. The engineering challenge was unprecedented. Retrofitting 450 Minuteman III missiles would cost $2.3 billion and require complete electrical system redesigns. Each missile would need to be removed from its silo, transported to specialized facilities, and rebuilt with new safety architectures that eliminated cascade failure possibilities. The project would take 3 years and involve thousands of engineers and technicians working under the highest security classifications. But the alternative was operating a nuclear deterrent with unknown failure probabilities. Williams's analysis suggested that routine maintenance procedures could trigger accidental detonations at other missile sites. The electromagnetic interference patterns that had caused the A-8 explosion existed throughout the Minuteman fleet, creating a hidden Russian roulette where any electrical test could potentially trigger catastrophic safety system failures. As Chen emerged from the contaminated silo after 2 weeks of investigation, he carried documentation proving that America's most sophisticated nuclear weapons were vulnerable to their own safety systems. The cascade failure at A-8 wasn't an isolated accident. It was a preview of systemic vulnerabilities that threatened the strategic foundation of nuclear deterrence itself. Major Viktor Petrov received the initial satellite intelligence report at GRU headquarters in Moscow 73 minutes after the explosion at launch facility A-8. The Cosmos 954 reconnaissance satellite had been conducting routine surveillance of American ICBM installations when its infrared sensors detected a thermal signature consistent with high explosive detonation in the Wyoming missile fields. The electromagnetic spectrum analysis showed patterns that didn't match any known American weapons testing protocols. Petrov spread the satellite imagery across his desk in the windowless analysis room beneath Dzerzhinsky Square. The photographs showed a massive crater where the missile silo had been, surrounded by emergency vehicles and personnel in protective clothing. The most revealing detail was the concrete blast door, clearly visible as a cracked slab hurled 200 feet from the silo opening. No routine maintenance exercise would require that level of explosive force. The radiation signature detected by Soviet monitoring stations in Kamchatka confirmed Petrov's initial assessment. The explosion had involved nuclear materials, but not a nuclear detonation. The gamma-ray spectrum was consistent with plutonium dispersal from a damaged warhead, suggesting either a transportation accident or a catastrophic failure of American nuclear storage procedures. What concerned Petrov most was the immediate deployment of 300 personnel in full radiation protection equipment, a response that indicated major contamination requiring months of cleanup. Within 48 hours, additional satellite passes revealed the scope of the American response. The cleanup operation involved specialized vehicles, temporary structures, and soil excavation equipment typically associated with nuclear accident mitigation. Petrov cross-referenced the activity patterns with declassified information about American nuclear transportation protocols and concluded that the United States had experienced a significant nuclear weapons accident that they were attempting to conceal. Petrov's analysis reached a different conclusion than the Americans intended. Rather than recognizing the explosion as a systemic safety failure, Soviet intelligence interpreted the accident as evidence of dangerous laxity in American nuclear weapons transportation and storage procedures. The GRU's assessment suggested that American nuclear warheads were being moved or maintained without adequate safety precautions, resulting in accidental detonation of conventional explosives. This intelligence assessment had immediate strategic implications. If American nuclear weapons were vulnerable to transportation accidents, Soviet nuclear doctrine needed to account for the possibility of unintended nuclear incidents during periods of international tension. More critically, the apparent weakness in American nuclear safety procedures suggested opportunities for Soviet intelligence operations targeting American nuclear facilities. The misinterpretation cascaded through Soviet strategic planning. The Defense Ministry accelerated development of mobile ICBM systems, assuming that American nuclear weapons were vulnerable during transport between fixed installations. The Soviet Navy increased patrols of American ballistic missile submarines, anticipating that similar safety failures might affect sea-based nuclear forces. Most dangerously, Soviet nuclear engineers began modifying their own safety protocols based on what they incorrectly believed were American transportation vulnerabilities. Petrov personally briefed Defense Minister Dmitry Ustinov on the intelligence findings 2 weeks after the explosion. The meeting took place in the secure conference room of the Defense Ministry, with detailed satellite photographs and radiation analysis reports spread across the polished table. Ustinov studied the images of the destroyed silo and the massive cleanup operation with the keen interest of a former weapons designer. Major Petrov, what is your assessment of American nuclear weapons reliability based on this incident? Ustinov asked, tapping the photograph showing the crater where Launch Facility A8 had been. Comrade Minister, the evidence suggests serious deficiencies in American nuclear weapons handling procedures. The explosion pattern indicates that conventional explosives associated with a nuclear warhead detonated during what appears to have been a transportation or maintenance operation. The extensive radiation cleanup suggests that nuclear materials were dispersed over a significant area. Ustinov leaned back in his chair, considering the strategic implications. If American nuclear weapons are prone to accidental detonation during routine handling, this represents both an opportunity and a threat. An opportunity because their nuclear deterrent may be less reliable than they claim. A threat because accidental explosions could trigger international incidents that escalate beyond anyone's control. The Soviet response was swift and comprehensive. Within 30 days, the Red Army's strategic rocket forces had implemented new protocols for mobile missile operations, assuming that American intelligence was monitoring Soviet nuclear facilities for similar vulnerabilities. The Northern Fleet increased surveillance of American ballistic missile submarines, expecting to detect evidence of additional nuclear accidents. Most significantly, Soviet nuclear engineers began developing enhanced transportation safety systems based on their misunderstanding of American vulnerabilities. The irony was profound. America's cover-up had succeeded too well. By concealing the true nature of the Cascade safety failure, Strategic Air Command had prevented the Soviets from learning about electrical vulnerabilities, that potentially affected Soviet nuclear systems as well. Both superpowers were now operating nuclear arsenals with hidden failure modes that neither side fully understood. Soviet intelligence continued monitoring American missile installations for signs of additional transportation accidents throughout the remainder of 1978. Petrov's analysis team tracked personnel movements, equipment deployments, and radiation signatures across the entire Minuteman III network, looking for evidence that American nuclear weapons were systematically vulnerable to handling accidents. The most dangerous consequence was Soviet acceleration of nuclear weapons mobility programs. Assuming that fixed installations were inherently vulnerable to the kinds of accidents they had observed in Wyoming, Soviet strategic planners emphasized road-mobile and rail-mobile ICBM systems that would spend minimal time in stationary positions. The SS-20 Sabre mobile missile program received increased funding and priority based on intelligence assessments that American nuclear forces were unreliable during maintenance and transportation phases. As SALT II negotiations entered their final stages in the autumn of 1978, both superpowers were operating under fundamental misunderstandings about nuclear weapons safety. The Americans had learned that sophisticated electronic safety systems could cascade into catastrophic failures, but hadn't shared this knowledge with their Soviet counterparts. The Soviets had concluded that American nuclear weapons were vulnerable to transportation accidents, leading them to modify their own nuclear doctrine in ways that actually increased global nuclear risks. The explosion at Launch Facility A8 had created a hidden crisis in nuclear deterrence that neither Moscow nor Washington fully comprehended. Two nuclear superpowers were now basing their strategic planning on incomplete and incorrect assessments of nuclear weapons reliability, setting the stage for potential miscalculations that could prove far more dangerous than the original accident in Wyoming. General Richard H. Ellis walked into the Pentagon's sub-basement level C on September 15, 1978, carrying the classified technical analysis that would reshape America's nuclear arsenal. The Nuclear Safety Review Board had assembled in Conference Room 7, a windowless chamber lined with copper mesh to prevent electromagnetic surveillance. Around the polished tables sat nuclear engineers from Sandia National Laboratories, Los Alamos, Lawrence Livermore, and the Defense Nuclear Agency, each holding security clearances that granted access to America's most sensitive nuclear secrets. Ellis placed Chen's investigation report on the table alongside Dr. Williams's comprehensive vulnerability analysis. The documents contained technical findings that challenged 3 decades of nuclear weapons engineering assumptions. The cascade failure at Launch Facility A8 wasn't an isolated incident. It was evidence of systemic vulnerabilities that potentially affected the entire American nuclear deterrent. Gentlemen, the analysis from Wyoming reveals that our most sophisticated nuclear safety systems contain hidden failure modes that no individual engineer could have predicted, Ellis began, his voice carrying the authority of someone who had commanded nuclear forces during the Cuban Missile Crisis. Computer modeling has identified 847 similar electrical pathways across the Minuteman III fleet. Each represents a potential cascade failure point where routine maintenance could trigger accidental warhead detonation. Dr. Robert Henderson from Los Alamos studied the electrical pathway diagrams with growing concern. As chief designer of the Mark 12A warhead's environmental sensors, Henderson had personally certified that accidental detonation was mathematically impossible. The technical evidence from A8 proved that mathematical models couldn't account for the complex interactions between miniaturized electronic components operating in close proximity. General Ellis, if these cascade vulnerabilities exist throughout the Minuteman fleet, we're facing a complete redesign of nuclear safety architecture, Henderson said, setting down Chen's circuit analysis. The electrical interference patterns that caused the Wyoming explosion could theoretically occur at any missile site during routine electrical testing. The strategic implications were staggering. America's nuclear deterrent depended on 450 Minuteman III intercontinental ballistic missiles, each carrying warheads capable of destroying entire cities. If routine maintenance procedures could trigger accidental detonations, the entire foundation of nuclear strategy was built on dangerously unstable ground. Every electrical test, every guidance system check, Every routine diagnostic procedure represented a potential catalyst for catastrophic safety system failure. Ellis presented Chen's revolutionary solution to the assembled nuclear engineers. Instead of relying on 17 interdependent safety systems that could cascade into failure, the technical sergeant proposed 70 simple, completely isolated safety checks operating on entirely different principles: mechanical interlocks, electronic sensors, chemical barriers, physical safeguards. Each system would be designed to fail independently, making it impossible for a single electrical fault to propagate across multiple safety layers. The solution isn't more sophisticated electronics, Ellis explained, quoting directly from Chen's recommendations. It's simpler, more robust isolation between critical systems. We eliminate cascade failure possibilities by ensuring that no two safety systems share common electrical pathways, electromagnetic environments, or failure modes. The engineering challenge was unprecedented in scope and complexity. Retrofitting the entire Minuteman III fleet would require removing each missile from its silo, transporting it to specialized facilities, and completely rebuilding the safety architecture with new isolation principles. The project would cost $2.3 billion and involve thousands of engineers working under the highest security classifications. Every aspect of nuclear weapons safety would need to be reconceptualized from first principles. But the alternative was continuing to operate nuclear weapons with unknown failure probabilities. Williams's analysis suggested that the electromagnetic interference patterns responsible for the A8 explosion existed throughout the missile fleet, creating hidden vulnerabilities that could manifest during any electrical maintenance procedure. The nuclear deterrent that protected American national security was simultaneously the greatest threat to American survival. Ellis made the decisive recommendation that would end the crisis and reshape nuclear weapons safety forever. We will implement Sergeant Chen's distributed safety architecture across the entire nuclear arsenal. We will redesign every Minuteman III safety system to eliminate cascade failure modes. And we will establish new engineering principles that assume complex electronic systems will interact in unpredictable ways. The decision represented more than technical modification. It was a fundamental philosophical shift in nuclear weapons design. For 3 decades, nuclear engineers had pursued ever more sophisticated electronic safety systems, believing that complexity provided security. The A8 accident proved that complexity could generate vulnerabilities that no individual designer could anticipate or prevent. Implementation began within 60 days. Strategic Air Command established Project Guardian Angel, the classified program responsible for retrofitting the entire Minuteman III fleet with Chen's distributed safety architecture. The first modified missile returned to operational status in March 1979, equipped with 70 independent safety systems that operated on completely different principles and shared no common failure modes. The new safety systems prevented 4 documented near-miss incidents between 1979 and 1991. Each incident involved electrical interference patterns that would have triggered cascade failures in the original safety architecture. Chen's distributed monitoring approach successfully isolated these failures before they could propagate across multiple safety layers, preventing potential nuclear accidents that could have been far more devastating than the Wyoming explosion. By 1985, every Minuteman III missile had been retrofitted with the new safety architecture. America's nuclear deterrent had become genuinely safe for the first time in its operational history. The cascade failure modes that had nearly destroyed Launch Facility A8 were systematically eliminated across the entire nuclear arsenal, replaced by robust safety networks that could withstand multiple simultaneous failures without compromising nuclear security. The final vindication came in December 1991, when the A8 incident was declassified as the Cold War ended. The most dangerous nuclear weapons accident in American history had ultimately made nuclear weapons safer for everyone. The explosion that had scattered radioactive debris across 25 acres of Wyoming prairie had prevented far more catastrophic accidents that could have threatened millions of lives. Technical Sergeant Marcus Chen, promoted to Master Sergeant and assigned to Strategic Air Command's Nuclear Safety Division, had transformed a catastrophic accident into revolutionary improvements that protected human civilization from its most dangerous weapons. Nuclear deterrence required not just the ability to destroy an enemy, but the wisdom to control that power absolutely.